Hi, this is the May 2017 question, question 4b in hypothesis tests. It's a continuation of question 4b1. So we will be using some of the results we got in 4b1. Okay, so it was basically that there was this two assembly processes, the old process and the new process, and we were comparing their times. So you can see in the old process there are 11 numbers here, that's 11 pieces of data, so we'd say N1 is 11. And the new process, there are 9 pieces of data, so we'd say N2 is 9. These are the times in minutes it takes each process to finish a device, to build a device. So the other thing about this is that the populations are normally distributed, and you're asked to test at the 5% level of significance that the mean assembly time for the old process is greater than the mean assembly time for the new process. So we're comparing the means for both processes. Now that means we have to hypothesize. So our null hypothesis, H0, the null hypothesis, will be that there is no difference between the means. The null hypothesis is always that they're equal, that there's no difference. So we're going to say that mu1 is equal to mu2. That is our null hypothesis. The alternative hypothesis, H1, well, that's going to be what is asked in the question, that the assembly time for the old process is greater than the mean assembly time for the new process. So we're going to say mu1 is greater than mu2. Okay, so the null hypothesis is that they're equal, and the alternative hypothesis is that the mean for the first process is greater than the mean for the second process, the mean times. Okay, so that's that part done. Now then we could have a look at the tables and see the formula. We have all the data already. We have the means and the standard deviation and S hat as well from the previous part of the question that we did on the calculator based on these pieces of data here. So now the formulas are here on this formula sheet, which you will be given at the back of the exam paper. And you can see that the Z tests contain mu1 minus mu2 and x bar 1 minus x bar 2. The T tests also contain x bar 1 minus x bar 2 and mu1 minus mu2. So the decider is that when there are less than 30 pieces of data for one variable, you go with the T test. It's also called the student test. So it's when there's a small number of data. Okay, so in this case, for the first variable, there's only 11 pieces of data. For the second variable, there's only 9 pieces of data. So we could definitely use the t-test here. And the formula for the t-test I will write down now. T equals x1 bar minus x2 bar minus mu1 minus mu2 all over sigma hat on the square root of 1 over n1 plus 1 over n2. That's your t-test, okay? Now the thing about that is sigma hat has to be found. It's in the same page, sometimes not necessarily beside the formula. So sigma hat is the square root of n1 s1 hat squared plus n2 s2 hat squared all over n1 plus n2 minus 2. Okay, so that means we'll go ahead and use the calculator and find these. We're using the values that we found earlier. So n1 is 11, s1 hat is going to be 4.91. So I'll put these in. Actually, I'll write them down first of all. So sigma hat is equal to square root of 11 multiplied by 4.91 squared plus 9 multiplied by S1 hat 3.71 squared all over 11 plus 9 minus 2. So let's see what we get for that. On the calculator, square root fraction 11 multiplied by 4.91 squared plus 9 multiplied by 3.71 squared all over 11 plus 9 minus 2 equals 4.65. I'll just do it to 2 decimals because I've been doing everything to 2 decimals on this question. Okay, but for Paddy you might have to do it for 3 decimals. It really depends. Okay, so then the next part now is to find T. So we put the values we have. If you look here, the formula for t has mu1 minus mu2. That's the difference between the means. But according to our null hypothesis, the means are the same. The population means are the same. So that means that this would equal 0. So we can leave that out of the formula now. And we have x1 bar, which is 36.09 minus 33.44 over 4.65 times the square root of 1 over 11 plus 1 over 9. So let's calculate that. Fraction button, 36.09 minus 33.44 all over 4.65 multiplied by the square root of fraction 1 over 11 plus fraction 1 over 9. Okay, and we get 1.268, 1.27 for t. And this is our calculated from our data. Now what we need to do is compare this calculated value with the actual value from the t-tables. Now to check the t-tables, right, so the tables, according to the question, it's at the 5% level of significance, okay? And we need to know, is this a one-tailed or a two-tailed test? Well, it's one-tailed because we're only looking at the side where mu1 is greater than mu2. We're only looking at one side of the, right, if you were to consider this is a t-test, you could be checking this side, or you could be checking this side. If you're checking both sides, i.e. that mu1 does not equal mu2, mu1 is greater than mu2, or mu1 is less than mu2, you would be doing a two-tailed test. But in this case, we are only doing a one-tailed test here. That's 0 there. That's 0 for the t-distribution. We're only checking this side. Okay, so it's a one-tailed test. So we go to the tables, 5% and one-tailed. Now, you'll be given tables which are good tables at the back of the exam paper. Patty will leave them for you, but for now, I'm just going to have to use these old log tables, okay? So the other thing we need to know is we've got it's a one-tailed test. We know it's a 5% level of significance, and the other thing is the degrees of freedom. Now, sometimes he'll write that beside the exam paper. In this case, it's only 1 degree of freedom. It's going to be N1 plus N2 minus 2, which works out as 11 plus 9 minus 2, which is 18. So we're looking at T18 at 0.05, 5%, okay? And it's one-tailed. So if I go to the tables, see these tables here? They only give one-tailed. Okay, and we've got 18 degrees of freedom. So we go down the tables. We go down the tables 1, 2, 3, blah, 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 down here to get to 18. There's 18, and it's 5. The level of significance is 5%. That's 0.05. So 18.05. That gives us this 1.734. That equals 1.734. Okay, and they're pretty close. So, the t-distribution is similar to the normal distribution in that it is centered around 0. The only difference is that there's only maybe 30 items in it. It's quite small. So, this is our 0, should be centered. The critical value, according to the tables, is 1.734. The value we have from our data is here, 1.27, and it's in here, 1.27. Now this here area here, this area is the do not reject CT, hit 0, and in this area it is reject, hit 0. Now our number is 1.27, so it's less than 1.734, so it's in this side of the graph, so we do not reject, hit 0. If our number had been 2, it would have been greater than 1.73, and it would have been here, and we would have been rejecting our null hypothesis. But as it stands, we're in here, the number is in the do not reject region. So you have to finish the question off with a little bit of English, as in, we'd say as 1.27 is less than 1.734. Do not reject the null hypothesis. That means we cannot conclude that the means, so we could go back to the question then and look at this. We can't conclude this here. We cannot conclude the alternative hypothesis because we cannot reject the null hypothesis. So we cannot conclude that the mean assembly time, for the old process is greater than the mean assembly time is greater than mean assembly time for the new process. PROCESS. And the thing is, we have to state that it's at the 5% level of significance. We're allowing ourselves a 5% error to be, 5% chance that we're wrong. Okay, that's it. Thank you.